Good afternoon, everyone. When we talk about relative rate of change, it's basically what it says. It's the rate of change relative to the total. All right, so it's going to be defined by this equation, where we have the derivative on top and the total amount on bottom. Right, so this is your rate of change divided by amount. If you look at the answer key on Canvas, I kind of run through an example of where rate of change is not a great indicator a lot of times when you don't deal with the relative rate of change. Relative rate of change can show you that, well, this might be changing by $1,000. If you have $10,000, it's not a big deal. Whereas something changing by $10 when you only have 20, that's a pretty big relative rate of change. So just kind of take into consideration what you're dealing with and how big of an issue you have to start with. In this next example, I kind of forgot to mention. I'm going to see this is modeled by the function f of t is equal to 3.4 plus 0.04 t plus 0.13 e to the negative t. All right, so this is our function. We want to find the relative rate of change. So find relative rate of change after 1 year. All right. So what we would do is first just find f prime of t, which in this case the 3.4 is going to drop off. The 0.04t is just going to become 0.04. And then this last part, the 0.13, e to the negative t just becomes a negative 0.13 e to the negative t. All right, we're going to divide that by our original f of t, which is at 3.4 plus 0.04 t plus 0.13 e to the negative t. All right, with all of that, if I want to find the relative rate of change, in this case after 1 year, excuse me, I would just plug in t equals 1. That doesn't look very good. Let me retry that. T equals 1. All right, use your nice fancy calculator to figure this all out. And what you're going to end up with when you plug this in is about a negative 0.02. Sorry, 0.002. Which will correspond to a negative 0.2% or a 0.2% decrease relative to the total amount, right? So it may be decreasing by 60%, but it was at 120% beforehand, and so the relative rate of change there is different, okay? This next one's exactly the same way, or exactly the same thing, except we're going to use this idea down here, this derivative of a natural log, to help us figure this out, right? So if I was looking at this function here, and I wanted to find, I'm not going to go through the whole thing, it's looking for it after 5 years. I'll leave plugging in 5 for you to check on your own. All right, we'll do the first part. All right, I want to find f prime of t over f of t, which isn't going to be too bad, but it is a little bit more complicated when we look at this function. Whereas I know that this is going to equal the derivative of the natural log of this function, which may not seem that helpful. What's nice about this is that the derivative is easier to take when you take the natural log, right? So if I look at the natural log of 750,000 e to the 0.6 square root of t, this is actually the natural log of 750,000 plus the natural log of e to the 0.6 square root of t. This is going to be some number, so I'm just going to leave it as natural log of 750,000. This, because they're taking the natural log of e to some power, this is just 0.6 square root of t. All right, so when we take the derivative of this, all right, so now when we look at the derivative, d dx of the natural log of 750,000 plus 0.6 squared of t. This piece, this first part, that has no variable, so it goes away. All right, so we're really just looking at the derivative of the second part, all right, which has a pretty nice and not easy, but easier derivative than some things, and so it's going to end up being 0.3 over the square root of t. All right, and so this whole thing can be done a little bit quicker. Again, not going to be a big deal with relative rate of change. I will stick mostly with polynomials when we're testing this. I will usually stick with that, but the idea is it's the derivative over the original function. You find it, you plug in whatever t value you want. So in this case, we're plugging in t equals 5. Again, I'm going to leave that for you to check. All right, the piece of information from this chapter that I think is more exciting is the elasticity of demand. All right, also, just so you know, I haven't said anything. This is 5.3. All of this is 5.3 in your textbook. All right, but elasticity of demand is really going to tell us how susceptible or how much demand changes when price changes. And so really what we're going to look for is, oh, can I change my price without affecting demand, right? If I increase the price, usually less people buy it. But what we're going to find is there's going to be a nice little spot where you can change your price and it's not, the same amount of people are probably still going to buy it, okay? And so there's a really, really cool way to develop this equation. If you look in the textbook, it's going to show you. I just don't think it's going to be very beneficial in this format. So what I will say is if I need to ask you for elasticity of demand, I will give you that equation. Even on the test, I'm going to have this sitting right next to the question. You use it, and really just going to be about finding these derivatives and plugging things in. If you notice, we have part of the relative rate of change in here already, right? So this part here, that is the relative rate of change. We're just multiplying by the negative price. But in this case, f of p, just so we know, is a demand curve, right? So we talked about this before. It's a demand curve, but now it's in relation to price. So it's sales determined by price. Right. And so what we're going to do is we're going to find the elasticity of demand. So we're going to go through a couple problems to find it. It's not too much. But this first question, what quantity can be sold at $30 per pound? This is just saying, well, what is our demand in response to $30 per pound? So what is F of 30? All right, well, it's just 100 minus 2 times 30 coming from this equation up here. All right, well, let me just show you this equation right here. When we look at this, we get 100 minus 60, which is 40, right? So that corresponds to saying you're going to sell 40 million pounds of this metal if you set the price at $30 per pound. That's kind of what the demand is saying. All right, so theoretically, if you increase the price, right, you're going to sell less pounds because less people really want to spend more money. All right, so now we're going to develop that E of P. We're going to use this equation to develop the E of P. So things we need to know is negative P, just our variable. We need to know F prime of P, and we need to know F of P. Now these two we technically already have. So the only thing we really need to find is that derivative. And luckily we're always going to be dealing with a linear function in this case, right? So here our F of P is 100 minus 2P. And so then our derivative, pretty straightforward, is just negative 2. There's not much to it. All right, so then when we develop our E of P, it's negative P times negative 2 over that original function. And we get that our elasticity of demand equation, let me rewrite that. Our elasticity of demand equation, E of P, is just 2 over 100 minus 2P. Okay? And this is going to be a nice little equation that we can use. It's going to say, do we want to increase price, lower price? Can we change price? What's going on here? And what we're going to see is that This is always going to give us a positive number. That's why we have this negative p over here. We make it negative to make sure it's always positive. Excuse me. All right, but the big delineation here is this number going to be above 1 or below 1. That's what we're going to look for, right? So let's compute the elasticity of demand for two different spots. Okay, so in this case, we're looking at for E of P at P equals 30. All right, so we're going to look at E of 30, all right, which is 2 times 30 over 100 minus 2 times 30. All right, what we end up with is 60 over 40, which is, I don't know why I'm putting the squiggly lines, this is exactly 1.5. Okay, and so what this corresponds to, the context of this is that a 1% change, a 1% change in price. All right, so we increase by 1% or 100%. We're boiling it down to 1% so the numbers work out. Corresponds to a 1.5% change. Actually, instead of writing change, let's write what these really are. A 1% increase, because we're not really going to worry about decreasing price. We could, but these would go to decrease here. Would correspond to a 1.5% decrease in demand. All right, and so our increase in price is having less of an effect as our decrease in demand, right? We don't want this 1.5 to 0.1 to 1. That's a bad ratio. All right, and so that's why we want this number, generally want this number to be less than 1. Okay, and we can see that if we look at E of P at P equals 20, that might happen. Well, it will. Let's just see why. All right, so E of 20 is going to be 2 times 20 over 100 minus 2 times 20, which is 40 over 60, which is about here I could put my squiggly lines, 0.67. Okay, and so what this corresponds to contextually is that a 1% increase in price corresponds with a 0.67 decrease in demand. All right, and so that's showing we have a good ratio, right? The price is affecting demand less, right? And so we can increase price without really losing too many sales. All right, so then what we're going to look for, I'm going to save, well, no, we'll go and do this one, is I will tell you I'll definitely ask a question like 5A on a test. It's finding the ideal elasticity demand. Where's the best place to sell price, right? Because if you're below 1, right here 6.675, that means we can increase price. We can make more money. If we're above 1, that means we've affected price too much and we're selling less. And so what we want to look for is, well, when does EFP equal 1? That is the ideal situation. This is the most effect size for this, and that's what we're going to solve, right? So we're going to take, in the same equation that we've been using, our EFP was 2P over 100 minus 2P. We're going to set that equal to 1 and solve. And luckily, the solving is not too bad once you kind of clear your denominators, right? We're going to multiply. Let me go ahead and write this a little bit bigger. All right, we're looking at 2P over 100 minus 2P is equal to 1. I'm going to multiply both sides by 100 minus 2P. All right, we get 2P is equal to 100 minus 2P. I'll add 2P to both sides. Clear that out. We cleared that out up there. All right, we end up with 4P. 4P equals 100. Divide by 4. Divide by 4. P equals $25. All right, so this says that if we set the price at $25, that's the ideal price. This price isn't affecting sales too much. We have highest we can set the price without affecting sales too much. So this will be where we ideally or theoretically make the most money.